Hello, everyone. Thank you very much to the organizers for inviting me to give this talk. Today, I'm going to tell you about some work in a paper that has not yet come out. It's still being drafted, together with Huanheng Qi, Henrietta Elvang, Aidan Herdeshi, and Shruti. And then towards the end, I'll make some brief remarks about this subject that Shruti just talked about and the content of this paper with Laura Johnson. Okay, so the major problem that I want to think about is the question of which models can be double copied. So which models admit a double copy structure? This means both which theories can I put into the double copy and what do I get out? And whatever mysterious structure is underlying the double copy, I want to know if it's rigid or does it admit continuous deformations. So one of the nice things about giving a talk at a conference like this, QCD meets gravity, is I don't have to work very hard to motivate why this is an interesting question. So I'll just submit that this is something that you might be curious about. So in this talk, I'm going to propose a framework for constructing generalizations of the familiar KLT formulation of the double copy for tree-level scattering amplitudes. So the reason why I'll be talking about things that are technically extremely elementary is because I want to begin by asking this question in a context where at least we think we have a complete understanding of what's going on. So I will motivate an organizing principle for thinking about this, which we call the minimal rank condition, for demarcating the space of bi-adjoint zeroth copies, which lead to a physical double copy, and also an associated perturbative computational technique, which we call the KLT Bootstrap, for generating deformed KLT kernels, which give a physical double copy. I'll then present some solutions to the Bootstrap equations, together with a probably infinite parameter family of open string-like solutions to the associated BCJ constraints, and analyze the generalized double copy. And then if there's time, I'll also comment on massive deformations relevant for Shruti's talk, and we'll understand why the naive massive double copy fails within the overarching framework of this, this organizing principle. Okay, so the starting point for this is the double copy in KLT form, and in particular in the KLT form that was given to us by CHY. So we learned many amazing non-trivial things about tree-level scattering amplitudes from CHY, and one of them was that the good old-fashioned KLT formula is hiding some hidden structure, namely that the momentum kernel that goes into the usual sum over orderings on the left and the right, alpha and beta, should itself be thought of as being related to scattering amplitudes. It's the inverse of some matrix of scattering amplitudes of some theory which is doubly color ordered. So it has two group structures, and you have a color ordering with respect to both of them, where in my notation here, A left and A right, I'll call the left and the right single copies, and MN I'll call the zeroth copy or the kernel. And I'm going to be pretty general. The only assumptions I'm going to make about these for now is that I have a single trace expansion, or in the zeroth copy case, a double single trace expansion. So the basic question is, and one of the reasons, so the reason why this this formula is nice is that there's nowhere to hide. Everything that goes into it is an object that we understand. It's a tree-level scattering amplitude. And so a natural question that we asked is, does any bi-adjoint zeroth copy lead to a well-defined KLT formula? When does this produce physical scattering amplitudes with locality, factorization, Bose-Fermi symmetry, etc.? Okay, it's the same formula again. Rather important in this subject is the rank. So to even make sense of this formula to begin with, you need to decide what this inverse means. And it can't just mean take the inverse of the matrix of all orderings, because that matrix doesn't have full rank. So whatever the rank is, typically less than or equal to n-1 factorial, you have to restrict to a full rank submatrix. But the final result can't depend on this choice. Otherwise, you're not going to get a result that is Bose-Fermi symmetric, has all the right poles, etc. And so you need to impose a condition that if you choose these orderings, alpha and beta, in different ways, you get the same result. And this leads to a set of linear relations among the scattering amplitudes that we all know and love. But from this perspective, these identities, which in the familiar case are the KK and BCJ relations, are sort of unified together or brought into one framework. And moreover, this CHY form of the KLT formula is prescriptive on this point. It tells you exactly what the modification of these familiar identities should be once you start to modify the kernel. Compare this with the string monogamy relations, which also unify these relations together into some sort of single set of identities. Okay, so the problem is, or the start of the difficulties, is that this formula is not manifestly local. So Shruti talked about a very similar, essentially equivalent manifestation of the same problem in the BCJ double copy, which is that at some point you're taking an inverse of a matrix, and there's some factor in that inverse which is the reciprocal of the determinant, and this determinant is some rational function, and in general it has zeros everywhere, all over the complex kinematic space, and this is going to produce non-physical spurious singularities in the final double copy. The second problem is that because we had to make this restriction on the space of orderings, you weren't able to take all of the orderings, that some of the factorization channels are going to be missing. So the double copied amplitude in general, just think of a gravity amplitude, will have poles in every possible channel. But if you start restricting which orderings you're summing over, then because you have these color order constraints and you can only take momentum channels with adjacent you can only factorize on adjacent particles, some of these are going to be missing. So let's see how does this work in the familiar case where we know everything works out. So the usual Bi-Adjoint scalar. So this matrix associated with this theory has rank n-3 factorial, as we all know. So the 4-particle double copy formula in this language looks like the following. And here you can see something remarkable, which is that these two problems cancel against each other. So if I choose the orderings on the outside to be 1, 2, 3, 4, then there's no way that these amplitudes can have a pole in the T channel. So that is the 1, 3 channel. And in general, I would expect my determinant to have some non-physical zeros. But here you find that the zero of the determinant is exactly the missing channel. So these two things sort of sum to zero or whatever. This point is even more dramatic if you look at the 5-particle example. So again, just pick two orderings, 1, 2, 3, 4, 5, and 1, 2, 3, 5, 4, and compute the determinant of what is now a 2x2 matrix. And again, you'll find that all of the channels that are missing due to the ordering constraints are exactly reproduced by the zeros of this determinant. So a miracle happens. There are no spurious singularities, and the determinant zeros always coincide with the missing poles. So if you're a very optimistic person, you might say, well, okay, I mean, maybe it just always works out like that. So maybe any deformation of the Bi-Adjoint scalar is just going to have this feature, and it will give a consistent double copy. So let's try. Let's just do something dumb, and let's just add a quartic term to the usual Bi-Adjoint scalar and just repeat the calculation. So I'm going to add this term with 4 phi's in it. So this immediately does something different. It changes the rank of the matrix to 2. So at 4 point, the generalized KLT formula based on this theory would look like the following. And so I can analyze the determinant of this matrix, and something terrible happens. You find that the determinant, numerator of the determinant has a 0 in it, and the 0 doesn't correspond to a physical factorization channel. It's at s plus 2t equals 0. So when I use this kernel for my double copy, my final answer will have a pole in that place, and there's just no way that can correspond to a physical scattering amplitude. And so it doesn't give a physical double copy. Okay, so what if you were a very pessimistic person? So I'll give you one example, but say you're very pessimistic. You might say, well, maybe there are no deformations of the cubic Bi-Adjoint scalar that can give a consistent double copy. But that can't be true, because string theory gives an example where it does work. So Sebastian taught us several years ago now that even the full alpha prime corrected strings KLT kernel can be interpreted as the inverse of some matrix of some higher derivative corrected Bi-Adjoint scalar theory. Here's an example of one of these scattering amplitudes. And they have this incredible feature that despite the fact that they have infinitely many higher derivative corrections, there's some conspiracy among these corrections in such a way that the rank remains n-3 factorial. So again, you can analyze the zeros of the determinant. You find that there's a missing pole, because there's a missing T-channel pole from the ordering constraints. And then there are indeed other zeros of this determinant, but they're all located away from the origin. So they're something that is sort of at the scale of the cutoff of my EFT, and so I can integrate them out. So at low energies, the double copy result is perfectly physical. So the secret to this, based on this and many other examples that we played around with, seems to be that what the strings kernel is doing that is special is that the rank does not change discontinuously as I take alpha prime to 0. Or more generally, the rank doesn't jump discontinuously as I change this continuous deformation parameter. So our proposal is to elevate this observation to a general principle. So this is what we call the minimal rank condition, that we propose that there should be a generalization of the KLT formula based on continuous deformations of the cubic bi-adjoint scalar, and that this should produce a well-defined double copy only if the rank of the matrix remains n-3 factorial. So there's a mathematically equivalent way of stating this, which comes from a fairly elementary theorem in linear algebra. The rank of this matrix being fixed to be n-3 factorial is the same as the statement that for all possible choices of gamma and gamma tilde, such that this matrix in the middle here is invertible, you should have some identity that looks like this. And this is not only a sort of friendlier version of this condition for implementing in Mathematica, it also has a simple physical interpretation. This is an instance of the double copy itself. And so the condition that you have to impose to get this minimal rank is that the bi-adjoint, or what in this case is the corrected bi-adjoint scalar theory, should remain the identity element of the KLT algebra. So 1 times 1 equals 1. So the procedure, and this is what I'll go through for the rest of the talk, is to begin, so to use the sort of general EFT bootstrap methods that people have been using for a while now, is we start by constructing a general ansatz for this doubly color ordered theory, solve the bootstrap equations order by order in that deformation parameter, and then construct a general ansatz for some single copy theories. In our case, it'll be Yang-Mills, but it could be something else, and then solve the associated generalized BCJ relations that sort of are implied by this corrected kernel. So there's a left BCJ relation and a right BCJ relation, and in general, they're different. Again, solving this order by order in the deformation parameter, and then use this to calculate a generalized double copy and see what we get. Okay, so let me take you through the analysis at 4 point. So for a general bi-adjoint theory at 4 point, there are 3 independent functions. They're given by these different choices of the 2 orderings. And what I mean is that all other orderings, either before or after this slash, can be given from these functions just by relabeling. And if you take those set of conditions that I wrote down on the previous slide, and you plug in these functions, f1, f2, f3, if you play around with the algebra, you can solve f1 and f3 in terms of f2, and then f2 is subject to some funny non-linear constraint that involves changing around st and u. So the procedure, and this is something very simple at 4 point, you could go away and do this in Mathematica in 10 minutes, is just to plug in a general ansatz for what is the familiar bi-adjoint scalar theory. So this is the usual uncorrected bi-adjoint scalar plus some general set of contact terms, plug it into this condition, and then match terms and try and find what are the constraints on these new Wilson coefficients A, K, R. And we'll do this order by order. So in the paper, we also solve the 5-point kernel this way. There they have 8 independent functions, and the calculation is more computationally intensive. But I'll present the results for 4 point, and then I'll make some general comments that are true actually in the more general case. Okay, so this is actually the result at 4 point up to 10 derivative order, and it's a whole mess. But the point is that that given any choice of these red coefficients here, this defines for your KLT kernel that has rank 1. So it has the same property that made the strings kernel special. It's not completely general. There are operators that are missing. So in particular, there could be a contact term here, a 0 derivative term, and that gets set to 0. So that's actually the naive deformation that I made before that I said led to a spurious pole. And so indeed, you find that it's 0. There are also other terms that are missing. There's no s to the 4 term here and so on. And the solutions to the constraints become quite complicated at high orders in the derivative expansion. So beginning at 10 derivative order, you get sort of complicated nonlinear combinations of the lower point Wilson coefficients. But anyway, so this is the general form of the rank 1 kernel. And as a point of comparison, let me write down on the same slide the same result that you get from string theory. And you can see immediately how much more general this generalized kernel is. So the strings kernel has a bunch of mysterious features that are way more restrictive than they need to be. One is that for this choice of orderings, it only depends on the Mandelstam S. And the second is that only odd powers of Mandelstams appear in the answer. So this general result is way more general than string theory.
15-minute mark, Callum.
Thanks, Joshan. Okay, so the second step is to take that kernel now and to figure out some theories that satisfy the associated BCJ constraints. So here I'll take what is essentially Yang-Mills plus higher derivative corrections, or some open stringy type model, where here again I have the usual Park-Taylor factor, and then some higher derivative terms that are parameterized by some blue coefficients E. And I solve the associated constraints. So this is actually the solution to the right BCJ condition. There is a similar but not identical solution for the left. So let me emphasize that point. So it is actually just an accident that in string theory and in the familiar KLT kernel that the theory you put on the left and the right in the double copy are the same. But actually in the generalized kernel, there's no reason for that to be. There's no reason these two different color structures need to have some interchange symmetry. And so in general, you get different solutions. So this is the solution for the right single copy. And you get a bunch of operators. There's some pole terms that correspond to some F-cubed operators. And then there are some higher point contact terms where I've written them down. And you see that there are some residual blue coefficients that correspond to these high derivative terms. These don't get fixed by the BCJ conditions, whereas other contributions get fixed entirely in terms of the coefficients of the kernel. These are the red coefficients. And let me just point out one interesting feature of this, which is that suppose I didn't know about deforming the kernel and I just insisted on using the usual cubic Bi-Adjoint scalar. What if I had just done the same computation? Well, that result that I get is just getting by setting all these red coefficients to 0. And if you look at this beta 3, which corresponds to this term over here, you find that sets that term to 0. So what that means is that this term, this term can never appear in a single copy if you don't know about generalizing the kernel. But if you do know how to generalize the kernel in the right way, you get a result or a single copy that is strictly more general. So again, you can compare this with the result from superstring theory. Here's the open superstring amplitude, and it's just some choice of these coefficients. But you get something that is strictly more general by taking these generalized kernels. And so in the paper, we've solved the BCJ conditions for the 5-point all plus amplitude up to D6 after the 5. Okay, and then the final step is to take these single copy amplitudes, to multiply them together in the KLT formula and to get some double copy. This is what we really care about. And you find up to some, I've written the answer out up to some order. Again, you get some set of operators, some factoring terms. Here you get some term with a dilaton exchange corresponding to the fact that dilaton parity is typically violated by higher derivative operators. And then some contact terms. And let me just make another interesting observation, which is in some sense is the opposite of the observation I made for the single copy, which is that for all of the operators that appear, not just here, but actually in all the examples we've calculated, if you shift the red coefficients, so the deformation parameters, then you can always compensate for that shift by a shift in the blue coefficients. These are the higher derivative corrections of the single copy. So in particular, you could always choose to set all the deformation parameters to 0 and still generate the most general double copy possible. So you don't miss any operators in the final double copy by turning all the deformations to 0. So this is a matter of taste. It might be simple for some application to work with a minimal KLT kernel that we're familiar with. For other cases, it might be more convenient to work with some deformed kernel. And as I said, this remains true up to 5-point, with up to operators that we've computed, which are of the form D8 out of the 5. And again, you can compare with the superstring answer, and there's not much interesting to say. You just get more interesting. You just get a more general result. So I'm running out of time, but let me just very briefly, this is my second to last slide, tell you something about a different kind of deformation that's worth considering, which is massive deformations. So here you can consider taking the Bi-Adjoint scalar theory and turning on mass terms. And the question is, can we use this to define a massive double copy? And what constraints should you impose on the masses and these couplings? So here I've actually introduced a flavor index on my Bi-Adjoint scalar. So Gij now runs over whatever flavor structure I've given this thing. And so what are the conditions on these coefficients and these masses so that the rank remains n-3 factorial? So the parallel of everything Shruti told you in her talk can be worked out in the KLT language, and it turns out to be totally equivalent to the BCJ double copy. And in that case, what we found was that if there's no flavor structure at all, so if all the particles are identical and have just one mass, then turning on the mass breaks the rank of this matrix to n-2 factorial. And as she told you, you find spurious poles in the KLT kernel for n greater than or equal to 5. So for 5 particle scattering and higher, just turning on a single mass gives you a non-physical double copy. Whereas you can think of something more general, and if you make this assumption that Shruti told you about, where you allow masses to different masses to run in different channels and different masses to be on the outside, but you make this sort of ad hoc assumption that you only have a single mass eigenstate in every channel, then you find that the rank of the KLT matrix is n-3 factorial only if the masses satisfy this spectral condition. And it's satisfied by KK theories, but it could be true in other examples, we don't know. And there's an open problem here, which is to find the general solution to these constraints. And there's a reason to think that there should be more general solutions, because string theory is a theory with massive states, and it double copies. So and it doesn't come from a dimensional reduction. So there's reason to think that there should be some more general set of solutions out there. Okay, so let me just summarize. So we've proposed an organizing principle, which we call the minimal rank condition, and a computational method we call the KLT Bootstrap for analyzing perturbative deformations of the KLT kernel. And we found a vastly more general stringy solution. There's strictly more operators allowed in the single copy theories, but the same set of operators appear in the double copy. It appears the minimal KLT kernel is enough to get the most general result. There are various open questions. One big one that came out of this conference is, could we understand this principle and this construction from the perspective of color kinematics duality using the methods that Suna talked about in her talk? Another natural question is, given that we started with a formula that was motivated by CHY, is this rank condition and these generalized kernels, are they somehow more natural from the CHY perspective? And then finally, we can talk about something which is more radical. We could think about discontinuous deformations of the kernel. And here we have some evidence that there may indeed exist a double copy, which is based on quartic graph structure, where you have a quartic interaction only Bi-Adjoint scalar theory, that at least to the examples we've calculated, does not contain any spurious singularities. So I'm over time, but thank you very much for listening.
Okay, yeah, so thanks again for Callum for a very nice talk. Okay, Lance.
Hi, Callum, thanks for a nice talk. When you say it's a stringy solution, do you mean that you think it comes from a string theory, or just that it extends to higher and higher orders in cutoff or something?
No, I just mean stringy in the dumb sense that the strings kernel has some special feature, that it has this low rank, and these are preserving that feature. So no, I don't expect these generalizations to come from string theory. I think that this structure is.
You can
I think there's some more general
somehow, or I don't know. Yeah.
No, I don't have any positive evidence that they don't. My intuition is that there's some more general structure that underlies this the KLT formula, and because string theory is a smart theory and it's consistent, it somehow is realizing that structure, but it's not the only thing.
Thank you.
James?
Yeah, thanks. Do you know sort of physically why how phi cubed and the string KLT kernel pop out? So you said I need to make the left and right color structures the same, but is there some other physical principle that will restrict you from your general KLT kernel to sort of the KLT kernels we know and love? Like what is the guiding physical principle to get you to go from the general case to the specific ones that we know?
Right. So you're asking what else should I impose so that my
Exactly.
general kernel reduces to the strings kernel?
Exactly.
That's a
And you
great
said-
question. I don't know.
You said one thing though, right? You have to make the left and the right colors the same.
I mean, yeah. So that is a true statement about those, but that's certainly not enough to uniquely.
Okay.
That basically says that your kernel is sort of a symmetric matrix.
Sure.
I would expect that whatever is picking out the strings kernel has something to do with good UV behavior. It's coming from string theory after all. It might have, the strings kernel is supposed to make sense not just as a low energy expansion. It's supposed to make sense, even once you include all of the massive string states. So if you don't integrate them out, but you take them seriously and keep them around, this is still supposed to make sense. So somehow that might be important. So if you thought about some kernel that was based on actually having exchanges of infinitely many particles in every channel, and you required some consistency in all of that, then you might find this is the only result, but we don't know.
Thanks.
Piotr?
Yeah, hi, Callum. Thanks for the nice talk. I kind of missed your statement that you made on the stringy KLT kernel having only S dependence first. And second, what happens when you restrict your run depth to only S power term? Do you have an infinite freedom, or is it one dimensional?
Yeah. So this is the statement is that when you take this particular off diagonal element, so then the kernel, it just depends on S for reasons I don't know. And I think the answer to your other question was no. I believe if I choose all the coefficients so that I set all the t dependent terms to 0 in this, I still have infinitely many free coefficients. Okay. So for example, here I still have some free coefficient.
Right. Thanks.
Alfredo?
Hi. Just a follow up to James' question. So, as we heard yesterday from Simon, in general there is an infinite set of EFT constraints that you can derive from unitarity or from the causality perspective, right? So the problem with that is that for massless theories, you have to be careful about the forward limit in general to derive these constraints. But I think, as we heard from Simon, there is a way to deal with this forward limit. So even for these massless scalar theories, you should get at 4 points an infinite set of EFT constraints. Maybe that's a way of constraining the 4-point kernel that you're looking at.
Yeah, no, I think that's an interesting idea. Although I'm not completely sure that the thing that comes out of the double copy, I would expect to have to satisfy various constraints like that. I'm not entirely sure that everything that goes into the double copy has to be physical. Like it couldn't violate these sort of positivity bounds, and then somehow, after you do the double copy, you get out something that satisfies positivity bounds. But yeah, something like that could be true.
Yeah, I wonder if you know that even the string kernel that you wrote down, I have heard is not unitary. Is not unitary in some senses. This 4-point stringy Bi-Adjoint scalar, right?
Right.
It would be interesting to see if that happens to pass the positivity bounds.
So I don't know about the positivity bounds on the low energy operators, but I can tell you that if you take this formula seriously as a scattering amplitude, it is certainly not physical. So it has an infinite series of poles at negative values of m squared.
Right.
So these are not physical. So if you just naively take this seriously, it looks like it's exchanging negative mass squared states. So there's something non-physical about the strings kernel.
Right, but you agree that the output, at least, it should satisfy some sort of positivity constraint.
Right. And actually, that's exactly what happens in the strings case. So the kernel contains an infinite series of non-physical negative mass squared states. But when you take the double copy, these cancel against the zeros of the Veneziano amplitude. And so there's some magic that happens where the non-physicality in the kernel cancels out before you get to the final double copy.
Sure,
Yeah.
thank you.
I just want to say one example where positivity bound is not satisfied is the spatial gate layout. So you start with the pi on Lagrangian, but once you square, you get spatial gate layout, which does not satisfy those positivity bound.
That's because it doesn't have an s to the 4. Sorry, it doesn't have an s squared term.
Pi to the 4, exactly.
Uh.
Pablo de Vega, do you still have a question? I think you raised hand before.
You talking to me?
Yeah, I think you raised
Yeah.
hand.
No, the question I want to ask, I mean, after all, after you do all this modification, the only consistent solution can be string theory. Do you exclude that? Do you think you can get something else? Or?
Well, I mean, it depends what you mean by consistent. I agree. If you're insisting on consistency at all energy scales or something, then probably the only solution is string theory. If you just forget about that and you're just interested in building general gravity theories with arbitrary higher derivative corrections, at least it looks like you can get many more solutions than just what string theory gives you.
Yeah, the question is to see if they are consistent. I mean, satisfy all the requirements. I mean, positivity and unitarity and so on.
Right, and yeah, you're right. If you start imposing things like positivity, then probably string theory is the only answer. But I don't know.
Thank you.
Maybe last question, Julio.
Hi, thanks for a nice talk, Callum. So you mentioned that it's sort of a matter of taste whether you want to think about deformations of the kernel or of the single copy, if you want to generate the most general high dimension like corrections to some gravity theory. But does this new perspective give you a nice way to check if some operator will be compatible with the double copy or not? Which, as far as I know, it's still like you need to check if the like double poles cancel or if it satisfies the BCJ relation. So is there another way to tell from this new perspective?
Well, there's nothing more efficient than well, here's the relevant slide. So there's nothing more efficient than just doing this computation for the totally general kernel and just seeing if that operator is allowed in the list or not. Yeah. So, well, if the generalization that I proposed was the sort of all-encompassing generalization of KLT, then if your operator doesn't appear in this list, and you'll conclude no, it can never be double copied. But yeah, this would be the procedure. It's kind of labor intensive, but